right. Since you're both here, let me get started. Uh, I'm gonna, for this class, also post screencasts on the YouTube channel, and this is, partially for your benefit, but more so for my benefit. Plus, also I want to try to create some courseware content out there on the internet because it's generally useful. Folks have been telling me, and so there is a project that is out. It's out on the course Blackboard. It's due in a week. And for the project, you'll be implementing perceptron learning rule, and it's to reinforce the anatomy of a learner, which is what the focus of today will be. Okay? All right. This course mirrors a MOOC, a massively online course given by Yasser Abu Mustafa, who is a really big name in machine learning. He's a full professor at Caltech, or California Institute of Technology. And the approach that I like about his book and the version of the machine learning course is that he teaches it from the perspective of what I like to call the physics of learning. Right. So in this course, what we'll do is get through all the material about the physics of learning, and with the balance of the semester, we'll spend that time going through some publications, looking at examples that people have implemented and done, and relate those examples to the various parts of the anatomy of a learning system. Okay? All right, so that is out. It's due in a week from today at the usual 11:59 and 59 seconds, and it will require you to use MATLAB. If you don't have MATLAB installed, we have a site license. Do you both have MATLAB? I know you have MATLAB. Do you have MATLAB installed? Okay, so what I will do is I will post on the Slack channel, and I'll also email to both of you through Blackboard the link to the site license. And so historically, what happened was that a lot of the different research labs and groups were purchasing individual MATLAB licenses. And MATLAB is a mathematical modeling tool. It's very similar to Python in its language syntax. And I like to say Python is similar to MATLAB because MATLAB was around a lot longer than Python. But where it really shines is in vector matrix manipulation, as well as the choice as of the APIs that are available for it, so-called toolboxes that provide a lot of very useful functions that free you from all of the details that you shouldn't have to worry about when you're doing mathematical modeling types of applications. And so when you're multiplying matrices, inverting matrices, doing all sorts of stuff, eigen decomposition and so forth, MATLAB has some very nice, powerful libraries in which to do that. And so we found that all the research labs and different groups in the department were purchasing licenses of MATLAB, and that the cost summed across all of those labs was more than the cost of a site license. And so Dr. Asamni just decided, okay, why doesn't the department, and it was before it was the division, before we merged, why doesn't the department purchase a site license? And so with the site license, the nice thing is you as a student don't pay for MATLAB just by being a DSU student. You go to the website specifically for DSU site license for MathWorks, and that's the URL I'll send out to both of you. And you download MATLAB, and you can have access to all the so-called toolboxes, which are individualized API tool sets. And so these tool sets are based on certain type of topics. So there's like a financial time series toolbox, there's a robotics toolbox, a computer vision toolbox, a statistics and machine learning toolbox, and so forth. And so it's really nice because as a student, you have access to everything that they make. And MATLAB is made by the company called MathWorks, and they're award-winning customer support and excellent tutorials and videos and stuff like that. And so if you were to go on, the open market in industry, not as a student, and to buy from MathWorks what you have access to now as a student, it would literally cost you tens of thousands of dollars. And so even beyond just what you need for this class, I always encourage people while you're a full-time student to download MATLAB, and if there's something you're interested in, hey, tinker with it. Look at some of the tutorials and download it. For example, there's multiple person tracking using the deep learning MATLAB toolbox and stuff like that. So I'll send that URL out, and you'll need to install the MATLAB, and I'll tell you which toolboxes in the email to download with it. Okay, so you have the MATLAB toolbox, and what you'll be using is MATLAB to implement the perceptron learning algorithm, which we'll talk about today. So, machine learning. Well, now deep learning is pretty popular, and people say, oh, there's machine learning and there's deep learning, but deep learning is just a form of machine learning, right? It's nothing more than a glorified neural network with some very clever mechanisms for making the training more efficient. And what you learn in this class is a general framework in which you can pose a neural network, among other things. But this is a general machine learning course. And a deep learning network is nothing more than a particular function class or hypothesis set, which will make sense after today when I use those terms. And so machine learning is a branch of AI, or artificial intelligence, and is concerned with the design of algorithms that allow computing systems to modify behaviors or to improve their performance as they get more data from sensors or databases. And so this idea of improving their performance based on data, the more data you feed it, the better it gets. Now, one of the things we'll characterize in a very formal way is what quality and what better means, right? And so regardless of what type of machine learning algorithm you're using, it's really important as a scientist and as a practitioner because, as master's students, you're pivoting, you enter a student and you leave a scientist, right? And so our job is to bend you whether willing or unwilling, into being a scientist. And so, what I hope you to have an appreciation for at the end of the semester is an understanding of the physics of learning. If I change this, what's the consequence? If I change that and put these two pieces together, what's the consequence? And you'll find in many cases in machine learning, there's this natural tension between two competing factors, right? If you have a complex model, you have to pay for that complex model, and how you pay for it is with needing more data. What happens if you have more data? Well, you have to relax the accuracy, right? Nothing comes for free in machine learning. And so part of becoming a good practitioner, a good scientist as it pertains to machine learning is understanding what these competing factors are, what the physics are of a learner, and that helps you to build better models. Okay? All right. So that's what machine learning is. And of course, if you have the book it's a small book. It's an inexpensive book, and the author, and I subscribe to this as well. He made a point that the book should be relatively inexpensive. I think it's $20 or $30 on Amazon. Not this highway robbery of $200 in the bookstore. And so the reading for what I'm going to talk about at the outset will be chapters 1 through section 1.3. Okay. So the idea of machine learning is really, the realization of a crazy dream, crazy idea that people had in the 40s and the 50s when they're trying to understand how people think. And if you think about what a computer is and what a computer does, machine learning is really just a kind of mechanized learning system, right? You're laying out an algorithmic process that allows you to understand this idea of patterns within some information, right? The mechanization of a learning system. And so there are some examples of what I like to call machine learning in the wild. And these machine learning systems in the wild often consist of three major components. The first of which is data, all right? And let's take the example on the top. You have web pages. A web page has text, it has links, it has sections, it has video, rich media. It also has links to other web pages. And so a web page is considered semi-structured document. It's a type of document that has a little bit of free form, a little bit of structure to it. And it also has hyperlinks to other documents. So when you look at autonomous cars, they also traffic in data. Granted, that data is different from the data in a web page. You have video, you have LiDAR, laser range, you have radar, you have video, all sorts of stuff. The inertial measurement units for the speed. And then you also have what's called a model. And a model is that mathematical description of what phenomena you're trying to describe as it pertains to the data. So in the case of Google search or web pages, there's the so-called PageRank algorithm that employs a model, and that model of the internet is called the internet graph. So a node would represent the content of an image, of rather a web page, and the edge would represent the hyperlink. And so, for example, the Google PageRank algorithm, and the original algorithm is there. If you want what they're doing now, you have to get a job at Google and join the PageRank team, right? It's a trade secret what they're doing specifically. But the idea with a Google search, and when Google came along, it was a form of statistical search engine, but they do this called relevance ranking, and they use the edge structure in the graph to modulate the importance of a page. And if you think about the internet, if a page is pretty important, a lot of people are going to link to it, right? And so they use a probability that they compute using the in degree of that internet graph for the web page structure to better the notion of importance, if you will, of a web page. And so initially, the quote unquote page rank algorithm did this. And it was the first algorithm that used what's called degree disparity to rank your pages along with the content. Because before that, a lot of these search engines, when you entered in a search term, it was just looking for that content in the documents using statistical matching. Okay? So here we have a model, we have a graph, and then we have an algorithm that operates on that model in order to get some output. When we look at the autonomous car, okay, well, we have the detection of events. We have dynamic information working from the streaming data. And so certainly in the streaming data, temporal information is really important. In autonomous cars, there's something called a scented Kalman filter, which takes your motion model or description of how you move along with sample data, and it uses that to match obstacles or things, landmarks in the environment against what's in a map in order to figure out where the car is. Monte Carlo localization. So in that, you use the streaming data, you certainly have models, and you have algorithms that operate over these temporal streams. So you have your data first and foremost, you have some model, right? You have some mathematical construct, and then you have some process that operates using that construct. And then, of course, you have your application. In the case of a Google search, the PageRank algorithm, you have a relevance ranked list of documents in order of their suitability to what that search need was when you entered something in the search bar. And in the case of autonomous driving, you have things like collision avoidance, or it can figure out where it is on a map in real time based on the sensors, matching what it sees around it to how it thinks it's moving with what is on the map. Okay? So we have our application, we have our data, and we have our model. So what we're going to do is peel back some of these and talk about very specifically the basic components and their interaction with one another and all the issues surrounding how they operate so you can make very strategic choices when you're implementing your machine learning models, as well as understanding published machine learning models in the research literature. Okay? Right. Any questions about this? Make sense? Yeah? All right. So for this course, learning from data is the primary required text. Everything else I'll just provide as papers and PDFs through the Blackboard website, and that's the primary text. It's available just about everywhere for about $20 or $30. And there's also a companion website. Now, this companion website will get you to the online courseware where there are video lectures from way back when, I think it was 2012, where Abu Mustafa is teaching it himself at Caltech. And you'll also need MATLAB. And again, I'll make a mental note and send that out after class, a link to the site license. Don't pay money for MATLAB. You get it for free just for being a student. But you need to use your DSU student email in order to get access to that. And I know you already have it, right? Okay. All right. So this course, of course, you're all here. And so you know where it meets and when it meets. And again, on those off chances where I need to end class 10 minutes early, I'll certainly let you know at the beginning of class. That probably happens a handful of times during the semester based on my personal schedule. And so a distribution of things. Well, we have an exam. We also have a final project. We have 3 projects, 3 homeworks, and certainly I encourage your class participation, not just because it's part of the grade, but also it's important to be able to understand this through discussion. Okay? All right. So what subjects will we be covering? We talk about the learning problem. What does it mean to learn? Learning feasibility. We'll jump into very quickly a simple linear model to motivate what learning is doing. We'll talk about error and noise and how they affect your learner and how you measure them. We'll talk about training and testing, the importance of them, and strategies for doing so. We'll talk about generalization, and this idea of generalization is really, really important. What you're after when you implement a learner is you want this learner, based on existing data, you want it to apply equally well to new data that it has not yet seen. And so this idea of performance on data that it has not yet seen is called generalization. The whole goal is to build learners that generalize well, meaning that they do perform very well when you give it data instances that it has not trained on. Okay? Some people like to call it interpolation. I don't like to call it interpolation, but you can think of it as a kind of interpolation if you want to pose it in terms of functions. Okay. Learning complexity will add some mathematical rigor that we can prove that measures how difficult a certain type of learning problem is. Akin to computational complexity or algorithmic complexity, learning has its own way of expressing the difficulty of learning. And what you'll find, if something is too complex to learn, you have to make some trade-offs. Either you have to decrease your generalization, your accuracy on new examples, or you need to get more data. Nothing happens for free, right? And so the VC bound and the VC dimension is a complexity measure for how you measure the difficulty of learning and whether or not learning is quote unquote feasible, meaning it generalizes well, okay? And we'll use probabilistic bounds to talk about that. And so we'll also talk about bias variance, which is another way of measuring complexity. And we'll define what they are and what you can do about them. We'll also talk about more complex linear models and this idea of overfitting. Now, overfitting is sort of where the rubber meets the road, right? This is what makes learning difficult. And we'll find a definition for it, but essentially at this juncture, overfitting is a model's behavior of trying to describe a pattern out of the noise, right? And so how you fix overfitting is with regularization. And we'll describe what regularization is and show some examples. Then model validation is another aspect. You can use that to choose the right parameters for your model. And we'll talk about the natural trade-offs that you get with machine learning in model validation. And then we'll relax this regularization, kind of open it up more generally, and use that to develop support vector machines, which is a type of learning machine. And what we'll show is that using regularization penalties, that you can get all sorts of behaviors from your learning model. And with this idea called a kernel, we can take your data and you can change it and take a very simple linear model and get it to draw very complex decision boundaries in order to classify or learn on very complex data. So we'll start out with something that seems like a very impoverished, very simple, not very powerful model. And by making some simple changes, we can see how we can get it to do lots of complex things. And in doing so, the cost you pay is for the simple linear model, right? Then we'll talk about Bayesian methods and something called expectation maximization, or EM. And then we'll look at some practical considerations and, as time permits, the research literature. Depending on schedule, I might relax some of the Bayesian stuff, but we'll certainly do expectation maximization, or EM. Okay. So if we were to group these together, the first three is really kind of introductory, setting the stage of what is learning, right? Because we talk about machine learning, well, what does it mean to learn? There's some key ingredients that we'll find that we need in order to perform this thing we call learning. Complexity analysis. That next few, 4 through 7, talks about what can be learned, because there's no magic solution. Some things you just can't produce a learner for it. And what the important part is not that you can't produce a learner, but what are the conditions for which you can learn something versus you can't. Now, of course, I hope after this course is over in 17 weeks on the calendar, when you see somebody implement and publish a paper, implement an algorithm, publish a paper, sometimes they'll say, we got 100% accuracy. Rubbish. That never happens. It does not happen, right? You should have that healthy dose of skepticism, but more importantly, be able to explain why, okay? But we're not there yet at this juncture. The next few, 8 through 13, talks about strategies for optimization. Can we improve learning? Now, improve it can mean a bunch of things. Can you make it so that the learner can learn more complex concepts? Can you make it so that the learner is faster or more efficient? Can you improve upon it? And then lastly, what can we do with all of this? Right? What types of things? And if there is there an overarching framework that we can use to think about how we do learning, particularly as we get to practical settings? Okay? Any questions about this? All right. So, what is machine learning? So let me ask you, what does it mean to learn? Everyone has their own opinion. What does it mean to learn? What do you think? Take a guess. Have you ever thought about that? What does it mean to learn? I learned. This thing learned. What does it mean to learn? What do you think? To know how to do something? So this know part, what does knowing mean? What is that? What do you mean by that? How do you learn? Remember what? You have to get information, right? There's something to be remembered. Okay. How about you? What does it mean to learn? What do you think? Mm-hmm. 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 Okay, so get an answer and then a technique and perhaps when to apply that technique. Okay, all right. So looking at the context of when to do something and knowing what the answer is. Okay, good. So we're going to define what it means to learn. And this definition that we're going to develop is going to be something that you can mechanize because there are lots of human examples and there are a lot of animal examples about learning. And you're both correct. All right. So an old example deals with the so-called Netflix prize. I'm not sure if you're aware of it, but a couple years ago, maybe 10 years ago, that's more than a couple, the Netflix company, video streaming company, decided to have an open competition. And they have a rating system, and this system, given your user preference, will come up with a rating to say or predict how much you might like a particular movie, right? Now, they said, okay, if anyone can take our data and can produce their own system to do movie rating prediction. And if you can implement something that can improve upon our existing algorithm by 10% or more, we'll give you $1 million. So I remember on the tail end of grad school, like, whoa, wouldn't that be great, right? Well, somebody already solved it. A group solved it, but it's still an interesting example. And if you look at these things called Kaggle, Kaggle, Kaggle competitions, they have lots and lots of open competitions similar to the Netflix prize. And in fact, it was the reason that Kaggle started was a forum for doing bounties, as it were, and that was inspired by the Netflix prize. That was the first time a company had ever done that. So of course, Netflix, they have a lot of movies and they have a lot of subscribers. And each of these subscribers has a profile based on what you like. Now, that could be explicit, you fill it out, or it could be just on what you watch. They can collect and build that profile based on the movies that you tend to select and add to your library and or watch. And so they have a lot of data. And to implement a learner, you need some very basic but necessary ingredients. One is you need data, right? So that's one of the things. You have to have data. If you have no data, you cannot learn. You can't, it's just impossible. So you could also kind of tweak that rule, if you will. If you have only a little bit of data, you're not going to learn very well, right? The more data you have, the more you can learn. But if you have no data, you can't learn at all. There's no magic with machine learning. So you have to have data, but there also must be a pattern that exists, right? If you've ever, maybe you're both too young, but the tube TVs before the LCDs. And I remember when I was a kid, you turn on the tube TV, and if there was no broadcast, you just see the random pattern, right? Now you wouldn't just kind of look at the random pattern and say, "Oh, that's the ocean during a storm," right? That's silly. There's no pattern. It's just noise, right? So there must be a pattern. And if you think about the Netflix prize, there is a pattern there because people who like certain types of movies are going to rate certain types of content highly, Or people, let's say if you don't like comedies, you hate comedies, well, you're probably going to give a low rating to comedies, right? So there's absolutely a pattern in Netflix ratings. And that's another point, a requirement for a learning system. There must be a pattern. It can't be random, it can't be noise. Okay. So we have to have data, a pattern must exist. And this third point is pretty important. It must be that you can't express this pattern mathematically, right? If you can express it mathematically, that's not learning. Just implement it, right? If it says zero point 0.3 times one thing plus zero point 0.7 times this, just implement that. That's not learning. It's perfectly fine to implement it. So where learning thrives is where you don't know mathematically how to express what this pattern is that must exist, and you also have to have a bunch of data, right? So if you're dealing with a problem and you study it and you say, okay, well, I want to implement the learning solution, but the bad news is we don't have data. Well, there's nothing you can do. You can't learn. Maybe it's not a pattern. It's just randomized. You know, the signal on the screen for a tube TV when there's no broadcast. That's not learning. Um, if you can express it mathematically, right? F equals ma. Don't learn it. Just implement it. If you know the mass and the acceleration, just implement it. That's not learning. So you have to have these necessary ingredients in order to learn. And this Netflix prize absolutely has those three ingredients. You have a pattern, okay? These ratings, this idea of the coincidence between someone's preference and the content of the movie. There's absolutely a pattern there. Cannot express it mathematically. I certainly can't. Maybe you can, but nobody can. So certainly, because you can have many different ways of associating preferences with content, you can't really. It's not a one-to-one function. It's really hard to think about what a function is. It can't express it mathematically, and you certainly have lots and lots of data, right? Lots of titles and many millions of subscribers. So the Netflix prize exhibits all these three ingredients. So absolutely, you can do learning for this problem to learn a better rating. Okay, so we'll start with the data representation. And this data representation consists of two vectors. You have a viewer vector describing a viewer's profile. And in this depiction, we have each position of this d-dimensional vector represents the likes. And these likes are descriptive of the different types of movies you might have. You might be a comedy, an action movie, a blockbuster. You might like Tom Cruise, a certain actor or actress or what have you, right? And so the larger the dot, the stronger the preference. The smaller the dot, the weaker the preference. And so here I'm just depicting graphically what would be a scalar number, right? And so likewise, you have a similar vector for each movie that's in Netflix, and that would describe the content. Now, certainly you could try to automate this, but this would really be people viewing the movie and scoring it in terms of these different ways of measuring movies. So if something is very much has comedic content, maybe it's an Adam Sandler movie or what have you, then you would have a larger number in this position for comedy. And likewise for the other attributes. So collectively, the top vector describes the viewer preference, and the bottom vector describes the movie's content. So you can abstract this mathematically, and here we have on the top a d-dimensional vector, x sub v, v standing for viewer. It's the viewer preference vector, and each position here in this d-dimensional viewer vector represents the preference for the user. And it might be a rating from 1 to 5, 1 to 100. It doesn't matter what the rating scale is, but there is a rating scale for each position in this preference vector. In similar fashion, for the movie, you can have a similar vector describing the amount of content. It could be how many minutes in the movie of content is some comedic interaction. It could be all sorts of things, but at the end of the day, it's a scale that represents the amount of a certain type of content for that particular movie. So collectively, that represents the entire movie. You could have a comedy that's also a blockbuster and so forth. Okay? All right. Any questions about this? Does that make sense? Okay. So of course, when you're doing a rating, of course, a rating is higher if the viewer preference coincides very closely with the content of the movie, right? If you prefer something and that movie has that, it's going to be higher. If you don't prefer something and that movie has a lot of something you don't prefer, the rating's going to be lower. So you might already kind of be thinking of where this is going. You can take these two vectors and basically do an inner product between these two vectors. And if these two vectors perfectly coincide, the precise amount of preference is the precise amount of content proportionally. You're going to get a value that's higher, right? Closer to 1, because the dot product of two perfectly coincident vectors is 1. If they're orthogonal to one another, there's no coincidence, the dot product is going to be 0. It could also be negative, right? So nonetheless, the rating is going to be the measurement of the coincidence between X sub V, our viewer preference, and X sub M, our movie content. And you can take a dot product with this representation, and the result of this is a rating scale. Now, of course, if this rating scale is a scalar between 0 and 1, you could absolutely reproject it onto 0 to 100 or 0 to 10 or 0 through 1 through 5 or what have you. It doesn't matter what the scale is. But we do have a way mathematically of measuring the coincidence between the viewer preference and the movie's content. Okay. Any questions about this? Does that make sense? So now we have a mathematical representation. Let's see what we can do with this representation to try to find a way to predict what the rating is given a certain viewer and given a certain movie content. And so what the learning is going to do is going to effectively reverse engineer the rating. So in Netflix, you have actual ratings. And what you want to know is what combination of factors, which positions in each of these vectors, the viewer preference and the movie content, is going to be predictive of this rating when you take the inner product. And that's essentially what you want to do, is figure out which combination of factors is going to predict it. So how was this done? And in fact, the solution that I'm going to describe to you was an actual solution that upon which is based the winning solution, right? And so you have some movies and some viewers, and you generate a large number of randomized vectors. So you're going to effectively create a fake movie and fake viewer, right? And you're going to do it many millions and millions of times. Okay, so now you're going to get a bag of movies that are generated, a bag of viewers that are generated, and you're going to take those, and if you took the rating, you'd actually get a rating. Okay, now if you go into the Netflix database, you have a bunch of actual ratings. Now, there are many ways to engineer a particular rating. So let's say you had a rating of 0.6. Whatever 0.6 means. It doesn't matter what the scale is. Between 0 and 1 means it's more coincident than less coincident. But let's say you had 0.6. There are many different ways you can describe the matching between the viewer preference and the movie content to get to arrive upon a 0.6 rating, right, out of that scale. So what they do is taking these large set of manufactured movies and manufactured ratings, they say, okay, well, let me take an actual rating from the real Netflix database. Now, given this actual rating that occurs, I want to take all my sampled movies and all my sampled viewer preferences and decide how I need to adjust them so that the rating of that sampled user and sampled movie approaches or matches an actual rating in Netflix. Does that make sense? So you have actual rating, and it doesn't matter what the movie is and what the viewer is for the actual. Now, when I say prime, that means that's the manufactured one. So you take a manufactured one, you get a rating. You take an actual rating, and there are different ratings that exist throughout that Netflix database, and you say, okay, what do I need to do to the attributes of this and the attributes of that in order for this rating to approach a real rating? And because I've done this manufacturing many millions of times, I'll find many, many different ways to manufacture what this rating is R. So what do? I have an R prime. I compare it to one of many ratings in the Netflix database. And I say, okay, let me now change these vector values a little bit. And I change them using a gradient such that this rating gets closer and closer and closer to an actual rating. And you do that a million different ways. And once you get a million different ways of getting this R prime to look like an actual rating, what you're left with is different types of coincidences that started out manufactured that will get you that 0.6. So if you do that with enough manufactured data, adjusting, what you end up with is a population of actual viewers and actual movies. But more importantly, you know how to get to a certain type of rating. Does that make sense? And so this was the basis of the winning entry for the Netflix prize. It's called Learning Vector Codebooks, if you want to ascribe a name to it. And it's a way of trying to find features and combination of features that will produce a particular outcome. Okay? So we started out with a learning problem. We have a mathematical representation, and now we have a way of searching through that mathematical representation to arrive upon some mimicking of a real process, where the real process is the population of actual ratings. Does that make sense? All right. So let's carry this to another example. And this other example is credit approval. And let's say this is a bank, a fictitious bank, and you want to automate the approval of credit. People will fill out applications, and the bank will either approve or deny credit based on the information from the application. And this bank has a lot of historical data. Maybe it's been operating for decades. And based on this historical data, it has applicant information, and it has records about whether that applicant was a good credit risk or bad credit risk. They paid their loan on time each time for the duration of the loan, or they didn't. Okay? So here we have a table of values. And this table of values, kind of like the Netflix example, these are descriptors or features that describe a particular applicant, whether it's online or in person on paper. So you might have a field for the age, you write your age, the gender, maybe annual salary, the number of years in residence. Now, there are certain questions in the US they ask on mortgage applications or credit applications that they think are good indicators of what a stable credit risk is, a good credit risk. So if you've been living someplace for a long time, you're not going to pick up and leave, right? You're most likely to stick around for a long time, more stable. You're going to pay off the loan. That's the theory. Years in job, well, if you've been in a job for a while, you have the funds, as it were, to pay off this loan. So there's all sorts of questions that they ask that collectively describe somebody who's applying for credit from a bank. Does that make sense? Yeah? Okay. So we take a vector representing all of this credit information, and each vector represents a particular applicant, and we feed that into the system, and this credit approval system outputs one of two different values: approve or deny. Now, in the US, there are reasons why it's a good thing to automate this, and there are also reasons why you wouldn't want to automate it. Now, in the US, based on the unfortunate negative history about credit lending in the US, the reason why it's good to automate this is that if someone is denied credit, you're required by law, the bank is, if they ask, and oftentimes they don't have to ask, if someone is denied credit, the bank owes you an explanation of why they denied the credit. And the reason for that has to do with discrimination and bias from decades ago in lending, right? So there are laws in place that say you have to say why they were denied if they were denied. So certainly with a machine learning model, if you deny someone credit, you can say, well, this is what the model did. There's no bias happening. The model said this, and this is why. But there are shortcomings with this automation, because somebody who might look on paper like they're a bad credit risk, it could be that they're a good credit risk. Maybe the salary is really low, but their family has been in the area for generations, and they never have missed out on a loan payment. They pay every single loan. So these systems can be flawed because they're automated. They can't make qualitative judgments that human beings can. And so oftentimes when you have an automated system, if somebody is just barely a deny, what they do is they say if it's a strong denial, then you accept what the system says. If it's a weak denial, you set that aside and let a human being review it to try to make the qualitative judgment. Okay? So there are reasons when you implement a learning system and you use them, it's not only important just to say, okay, celebrate, we have a learning system, all is good, to also think about, in certain disciplines, in certain domains, there might be laws in place that you have to follow, like in credit finance, but you want to think about what the impact is of these decisions because these things aren't perfect, right? So in using a learning system, you go off and have wonderful careers and you implement learning systems to do stuff. You want to think about the consequence of what the system is outputting, because if there's something that's a flaw, well, from a business perspective, the bank is not doing as well because they have fewer customers. But from a personal perspective, somebody who would have been a great credit risk is now denied a loan, right? Okay, so there are reasons why you might want to automate and not automate this process. And that's the takeaway. So let's take a look at this. We have our credit information for the applicant, and we can express that as a d-dimensional vector, where each position in the vector represents one of these measurements, like years in residence, the age, the gender, the amount of current debt, and so forth. So each one of these positions in this d-dimensional vector represents a feature, and a feature is nothing more than a measurement over that particular data point. Now, the data point here represents one applicant, because the applicant is going to be input to the system, his or her information, and it's going to say approve or deny. So we have our input, which is a d-dimensional vector, where the d-dimensional vector collectively describes our applicant, a single applicant for a single vector. And then we have our output, which is the approval or deny decision. Now, set capital X represents the set of all d-dimensional vectors, lowercase x. Now, capital Y represents the outputs. Now, in this particular case, we have two outputs, a so-called binary decision problem. Your outputs could be approve, deny. It could be +1, -1. For this class, we're going to assume +1, -1. +1 would be the approval, the so-called positive example of a good credit risk. -1 would be a negative example, the so-called deny case. Now, of course, from a binary decision problem, you can synthesize a k-way decision problem. And we can talk about that briefly, but we're only going to consider the binary decision problem for this class. So set Y consists of two pieces of information, +1 or -1, representing the possible outputs that we can have for this learning system. Now this part, the target function, that's a theoretical construct. It exists, but you don't know what that function is, right? That target function is going to be a function that inputs a d-dimensional vector, all the information on a particular applicant, and it's going to output one of these decisions, +1, approve for the mortgage, or for the, I keep saying mortgage, approve for the loan, or -1, deny the loan. And so floating out there in space is the target function. And this target function, it's the ideal credit approval formula. It's out there, but you have no idea what the true one is. So what we're going to do ultimately is try to find a function that we can think about and then say, okay, let me search through all the different ways I can express this function we can think about and try to find the one that best mimics this hidden target function. It's there, we just don't know what it is. And if you do know what it is, just implement it. Don't use learning, right? So what else do we have? We said at the outset that we have records. We have historical data. So maybe it's hundreds of thousands, maybe it's millions, maybe it's just 1,000, but we have records for all of the applicants who've been applied for credit for this particular bank. And so each lowercase x is a vector in d dimensions, right? So we have the first customer, the second customer, the third customer, and big N is the number of records that we have corresponding to the number of customers that have applied for loan or credit at the bank. Make sense? So for the first customer, their credit approval decision, we're going to call little y1. So this could be +1 or -1. Y2 is the decision for the second applicant that can be +1 or -1, so forth for Y3, Y4, and Yn. So here, sometimes in the literature, these are called labeled instance pairs. Each of the x's is a d-dimensional vector describing a customer, and each of the y's is the corresponding +1 or -1 outcome for the respective x. We use a subscript for the y's so we know which x this corresponds to. Okay? Sometimes you'll see in the literature x1, +1, x2, -1, and so forth. But these historical records are given to you, and in machine learning, in a learner, these labels on the historical records are thought of as being assigned by this target function. And this is the ground truth target function. You don't know what it is, but it's out there assigning a y1 to this. If you give me this customer, it's going to be +1. If you give me that customer, it's going to be -1, right? Ground truth, it's assigning these +1, -1 approval deny labels to each one of these inputs in your historical data. You just don't know what this function is. Does that make sense? Okay, so we have our data representation. We have our possible outputs. We have our hidden ground truth target function, and we have our historical data. And this historical data has labels associated with each of these inputs, approve or deny, but those labels are provided by the target function. You just don't know what that target function is. You also have this last part. It's called a hypothesis set. This hypothesis set is a category of functions. And an example of a category of functions is degree 10 polynomials, right? Imagine if you could have a degree 10 polynomial. You could have a degree 0 polynomial, degree 1, degree 2, degree 4, 5, 6, 7, 8, 9, and 10, based on how you choose the coefficients. So if you said the family of degree 10 polynomials, that's a whole bunch of functions, right? So the hypothesis set is a class or family of functions. And what your goal is to choose from among this class or family of functions out of your hypothesis set for the best function that will mimic the assignment of these labels to inputs that best mimics the target function's assignment of these labels to the inputs. Does that make sense? So that's what the learner is doing. But in order to find the best hypothesis out of that family of functions, you're going to have to search for it. And the responsibility for that search is called your learning algorithm. That's what a learning algorithm does. Okay, any questions about this? Yes? No? Make sense? Okay. So let's kind of depict this more schematically. So we have our ground truth target function. It's unknown. And going with the banking example, this ground truth target function for banking example would be our ideal credit approval function. It's out there, but we just don't know what it is. So it's merrily working behind the scenes, and for each one of our historical records, it's assigning an approve or deny outcome for each one of these customers that have come in the past. Now, our historical records are fed into the learning algorithm, A, in this circle here. And we also have a hypothesis set. These are candidate formulas. It's a large family of formulas. And this learning algorithm takes hypotheses in the hypothesis set and searches through them for that hypothesis that best matches the assignment of the target function. So you'll try a hypothesis, and then you say, okay, input x1, what does it say? Does it match this or not? Input x2, input x3, input x4. So what you'll do is then compare the output of a particular working hypothesis with the output of the original target function. And everywhere it is not correct, you call that an error, right? So you calculate all the errors for a given hypothesis, working hypothesis, and then you search for another one and see if you get an improvement or reduction in that error. So you keep searching until you get a final best hypothesis, and then you output that final best hypothesis among all the hypotheses you've visited in the hypothesis set, you being the learning algorithm, and then you output that, and that's called G. Now, you'll notice here in the schematic, I say approximately equal to. You're approximating the ground truth target function. Now, if it's 100% correct, okay, you're doing okay. And I only say okay, not well, because there are some issues involved. You need to make sure you have enough training examples because that's going to impact your VC dimension. And we'll talk about that in great detail towards the middle of the semester. Does that make sense? So one of the important things that you'll notice here is some of these components in the anatomy of a learner are in red, right? You might be wondering why. And some of them are in black. Now, those that are in red are things that you have no control over, none whatsoever. You can't control the unknown target function. It's out there, but you have no control over it. The historical data, you can't control that. It's just given, right? It is what it is. You can't control anything. Everything in black, you have control of, okay? You have control of the learning algorithm because you have control over the approach you use for searching through the hypothesis set, right? You have control over the hypothesis set because you can decide something like, is it degree 10 polynomials or degree 5 polynomials? You have complete control over the family of functions you're going to search through. And so the combination of these two things, the hypothesis set, the candidate set of functions that you're going to search through, and the learning algorithm that you use to search. Now, the learning algorithm, a result of this search, is it's going to produce this final best hypothesis G. And you want a final best hypothesis G that best mimics the hidden ground truth target function over which you do not have control. Does that make sense? And so the things in black you can control, and in terms of strict definition, the hypothesis set in combination with the learning algorithm, those two together are called the learning model, right? So when you say, I have the such and such learning model, you say, okay, well, what are my candidate functions? And what is my algorithm for searching through those functions? Does that make sense? Okay, so let me take a brief time check. Wow, that went by quickly. I have 25 minutes. Okay, so a solution is found by searching through the hypothesis set. Now, the way you search matters, right? We won't talk a lot about that, but the way you search does matter. Okay, and so I already said learning model. Okay, so let's go past this. So here are some examples of miscellaneous learning models. So you all know deep networks. You've probably heard the term before. Well, a neural network is nothing more than a special set of functions. If you've ever done neural networks, it's a function of a function of a function. So it's a class of compositional functions of weighted sums, right? That's all a neural network is. It's a type of hypothesis set. It's a particular form of function. That's all a neural network is. Nothing special about it. Now, backpropagation is the method using gradients for searching through the set of weights for the weight that minimizes error. So backpropagation is the learning algorithm that searches for a particular type of composition of weighted sums that minimizes the difference between that function, or finds the best hypothesis that most closely mimics the ground truth target function. So the neural network is a class of functions, and backpropagation is a learning algorithm that searches through the space of weights. Okay. You have support vector machines. All a support vector machine is a maximum margin penalty, right, for finding a linear hyperplane. It's a type of function. It's a linear function. And you might make it nonlinear through a kernel operation, but it's just a type of function. It's a type of hypothesis. And then quadratic programming is the way you search through the space of functions. That's all it is. Decision trees. It's a type of classifier, but it's a type of function using hierarchical splits. Let's see, I just lost. Gain ratio splitting is the way you search for which split you're going to use for those split-based hierarchical compositions. Multi-frontier optimization. You're doing optimization by considering different encodings that they call genes, but a gene is just a type of solution. So it's a type of function, and you're evaluating this function in multiple places in its domain, And the genetic algorithm is the way you search through it, right? You do some mutation, you do some elitist selection. It's just a search mechanism, but you're searching in multiple places at the same time. Regression, it's a linear model, and it's just a weighted sum of terms. It's a type of function class, and stochastic gradient is the way you search through them. Bayesian network is a probabilistic model. A probability is a type of function. It's a special type of function, but it is a class of functions. And belief propagation is how you search through the probabilities for the probability that best describes the data that you have, the association between the feature vector, the applicant, and the approved deny decision, right? So Markov chain Monte Carlo, it's a type of function that looks at transitions from one state to another. Metropolis Hastings algorithm is the way you search through it. So I won't roll off all of them, but these learning models is nothing more than the combination of a particular type of function, your hypothesis set, and a way of searching through them. Nothing more, nothing less. Okay? So what I hope that you walk away from at the end of the semester, walk away from this class with sort of a, an eye of that's all, right? And that's why it's important to understand the anatomy of a learner, because when you go off to the literature, you'll ask yourself, what type of hypothesis set are they posing? What type of algorithm for searching are they posing? Now, you can take the same hypothesis and change the learning algorithm and get a better performance under the right conditions. So that's why it's so important to take the approach of learning the physics of learning, which is in contrast, if you look at, there are lots of machine learning courses online, right? But a lot of them jump into the algorithms before you understand the physics, right? Now, of course, my undergrad was in electrical engineering, right? And in electrical engineering, you don't build a circuit until you analyze what you want it to do. And you have to understand how electricity works and what you want to get out of it. But for some reason, in machine learning, people often start with the let's get it to do something before you understand how it works. So, like Yasser Abu Mustafa, the author of the book we have for the primary text, I subscribe to this method of learning the physics first before you look at algorithms, the behaviors. Okay? Because you can only understand the behavior once you understand the physics that defines the interactions among all of these components. Does that make sense? Okay, so of course, what we'll learn is how certain properties of these things, these components, affect the outcome of the resulting learning system that you build. Okay? All right. Any questions about this? No? Okay, so these are some examples, and this is just a very, very small. I could go on for 10 lectures just talking about this. Now, in pattern recognition, we spend more time looking at specific algorithmic implementations. But in this class, we spend more of our time understanding the physics. Okay? All right. So let's take a simple example, and I don't think we're going to finish today, 526. So let's take this credit approval problem. So we have our input vector in d dimensions, where each one of the positions in this vector represents an attribute for a customer, like the age, years in residence, existing debt, salary, and so forth. And let's define t to be a threshold. And this threshold represents a score, and this score is associated with the credit approval. So we're going to also define our model as a set of weights w. So we have x1, x2, x3, up to and including xd. We also have w1, w2, w3, up to and including wd, right? Now, we're going to take our attributes for our applicant, and we're going to multiply each attribute by a unique weight for that particular attribute. And so we take the weighted sum. We have the sum for I goes from 1 to d of the ith attribute xi times the ith weight, right? And we produce that weighted sum. And we sum together all of those weighted terms, and we check them to see if the resulting score, weighted sum of all the attributes, is greater than threshold t. Does that make sense? And if it's greater than threshold t, we're going to say, all right, approve the person for credit. Their aggregate score, or weighted sum, is greater than that threshold for some definition of threshold. Does that make sense? It doesn't matter what these values are. Likewise, if the weighted sum of all these attributes is less than the threshold, we're going to deny that person for credit. Okay? All right, yes. W are weights. They're scalars, real valued, and it doesn't matter what they are. You randomly assign them in the beginning, but you have a set of weights, a unique weight corresponding to each position in the input vector. So if we had three attributes describing an applicant, we'd have three weights: W1, W2, and W3. Okay. So you have a d-dimensional input vector. You also have a d-dimensional weight vector. Okay. All right. Any other questions? All right, so what we're going to do is we're going to call this thing our hypothesis. And how we're going to rewrite this is we're going to subtract t from both sides of the inequality, right? Bless you. So if we subtract t from both sides of the inequality here, we approve credit if the weighted sum minus t is greater than 0, right? And we deny credit if the weighted sum minus t is less than 0. And so we have a function, and it exists in MATLAB, called sine. Now it's SIGN. Is it positive or negative? Not the trigonometric function like sine, cosine, what have you. We can rewrite this decision as our hypothesis, and it's equal to the sine of the weighted sum minus the threshold. So sine, if the term inside of the sine function is positive, it's going to return a +1. If the term passed to sine is negative, it's going to return a -1. So now we have a mechanized method that this h of x, if you give it one of these x vectors, it already has a w parameter associated with the hypothesis, and it's going to return a +1 or a -1. Does that make sense? So now we have a functional form for our approval and our denial. Now, of course, I talked about this idea of a hypothesis set. So if we had an H where all that W1, W2, W3, let's say they're all 1, right? That would be a particular hypothesis. If I choose a different hypothesis, that would correspond to a different set of weights. Maybe W1, W2, W3 is 1, 5, 7 instead of 1, 1, 1. So as we visit a new hypothesis, what we're doing is selecting a new set of weights because the weights uniquely define the hypothesis. Does that make sense? So now we have a mechanized function. We can implement this in something like MATLAB for describing what it means to approve or to deny credit. Okay? All right. And so we have many hypotheses because we have many instantiations of our weight vectors. So you try a hypothesis and see how it works relative to the target function, and then you try another one, and you hold on to the best one over some period of time. Okay? All right. So let's clean up the math a little bit. So we have this expression for our hypothesis, the weighted sum minus the threshold, and we input that to sine. Okay, and sine can return +1 or -1 depending on whether the parameterization to it, the parameter, was positive or negative. So let's now clean this up. So we're going to take our threshold. Remember, it was minus the threshold, right? The weighted sum minus the threshold. We're going to replace this negative t with a W0, a W0. Now, W0 is going to be minus t. And we're doing this because we want to clean up the math to make it easier to implement. So in the previous slide, we said sine weighted sum minus t. In the next slide, we're going to replace this minus t by plus W0 or W0. Does that make sense? Yeah? So instead of writing sine weighted sum minus t, we're going to replace minus t with a W0. So we write plus W0. Okay, so now we're also going to add a dummy variable. We're going to add a variable called x0 or x0, and x0 is going to have a constant value of 1, right? It's always going to be 1. And so if we do that, well, multiplicative identity says we multiply something by 1, it doesn't change. So we can write this plus W0 as plus W0 times x0, right? Doesn't change the expression mathematically because we've defined x0 to just be a constant 1, okay? All right, so now if we look at this expression, we say, hey, wait a minute. Here we have an index of 1, but here we have a 0 index and a 0 index. Let's absorb this term into the summation. So we change the index. It used to be 1. We're going to change it to 0. So now we write the sum, instead of from 1 to d, we say the sum, I goes from 0 to d, of wi times xi, keeping in mind that w naught is minus t, and x naught is fixed to 1. Does that make sense? Okay. Now, x naught didn't exist as one of our customer records. It's added to your data. So we start out with d dimensions, as we said before, right? X sub d. We're going to add an x naught. We're going to augment our vector, right, with an x naught, and it's always set to 1 because it helps the math work out. So you start out with your data, and you augment it by adding a new vector position in the beginning, and you call that x naught, and it's fixed to value 1 for all the vectors. Does that make sense? Okay, so now, that being the case, we have this expression, and instead of d dimensions, it's d plus 1 dimensions as a model. Now, once you're done learning, you bring it back to d dimensions when you want to draw it and see what it looks like. Okay, so in this expression, this is nothing more than the inner product between two vectors. Now, these vectors are of rank d plus 1, no longer d, because we added that w naught and that x naught, right? So if we were going to write this in vector matrix form, the sign of this weighted sum is nothing more than the sign of the inner product between the w vector and the x vector. And it's important to remember this w vector has a w naught, w1, w2, up through wd, and this x vector has an x naught and an x1 in the original x1 and x2 and xd. Does that make sense? So now you can do this in one line of MATLAB, and there's your classifier. Okay? So this thing will do is you input an x, you augment it with x naught, and then you take your w and compute sine w transpose x, and it'll either return a +1 for an approve or a -1 for deny. Now, the w defines the hypothesis, so if you want to change the hypothesis, you search for a different set of w's and compare the performance against the ground truth target function. Does that make sense? Okay, so I have 10 more minutes. So if you change the w, what is happening? Now, this w is a linear model. And remember, we started out with W1, W2, W3, W4, and so forth. The W naught was just the threshold. So what we're doing here, if you change your W's, well, in the plane, a linear model is just a line. In more than 2 dimensions, a linear model is called a hyperplane, right? So essentially, if you're talking about a 2-dimensional model, linear model, if you change the weights, what you're doing is you're selecting a different line. Because remember, in the plane, a line is y equals mx plus b. You have slope and y-intercept. If you change the weights, the slope and the y-intercept, you're changing the line. So what does it mean to search a hypothesis? To search a hypothesis space means to select a different w. Wow, this thing's hot. If you select a different w, what you're doing is you're selecting a different line. So as your learning algorithm searches through the set of hypotheses, what it's doing is it's trying out a different line to see if it agrees with the classification of the ground truth target function. So in this diagram, and you'll see this diagram a lot throughout the semester, you'll see data points, and the first feature is a projection along the horizontal axis. The second feature is projection along the vertical axis. Now, of course, for classroom perspective, it's only feasible to draw 2 or 3 dimensions, and it's a lot easier to see 2 because 3 you have to say, okay, imagine that third dimension. So you only see 2 dimensions because it's easy to see. So you'd have 2 features, the first measurement and the second measurement, and then the ground truth target function, if it were an approval for a loan, it would be plus to represent that it's a positive example, +1. If it's a denial, it'll be a minus representing that it's a -1 ground truth denial, okay? So here, if you choose your W1 and your W2s, in one case, you have this line. Now, of course, when you search through the space of hypotheses, what you're searching for is the hypothesis that separates your data in a way that most closely coincides with the ground truth target function. When it most closely coincides, what you'll see is the number of places where it has errors is going to be smaller, right? So you're constantly trying a certain set of W's, trying a W, okay, trying another W, did it improve? Try another W, did it improve? And you notice here, you have an error here. This should be on that side. You have an error, you have an error. Here, it's correct. All of the minus points, the negative ones are on this side, all the positive ones are on that side, right? And so that's exactly what a learning model is doing. Now, this line has another name that you'll find in the literature. It's called the decision boundary. Now, this decision boundary is a function that defines what values of the features corresponds to a certain labeling, right? Plus or minus. Does that make sense? Okay. So in this vector matrix form, now we have a very compact and very elegant way to define a working hypothesis. But we haven't talked about the algorithm yet. And you notice here, as I said, as you change the W's, you're changing the hypothesis. Changing the hypothesis means selecting a line. And when you search through the set of W's, you're searching through the space of hypotheses, looking for a line that best separates the data, i.e. that minimizes the errors, okay? So we have this hypothesis, sign W transpose X, and then remember for each Xi, we have the ground truth Yi. We have X1 and Y1, and that Y1, Y2 was the ground truth class label assigned by the target function, the approval denial decision from the historical data from the bank. So we have our hypothesis. We initialize our weight vector just randomly, and we have our ground truth training data from our historical records, where these W1, W2s were already assigned by the target function, right? You don't have control over that. So you start out with initial hypothesis, assign your W's randomly, and then you have your training set, which is historical data. You run each one of these input records, these users, through your hypothesis, and it's going to output for each one either a +1 or a -1. If the +1, -1 output from the hypothesis for this matches that +1, -1, it's correct. If it doesn't match, it has committed an error, right? So what this perceptual learning algorithm does, it says, go through my hypothesis, run all my data through the hypothesis, and select randomly, or you can have some other scheme, select one of the misclassified inputs. So select one input from the historical data where the hypothesis did not match the ground truth. And you're going to update that weight for the hypothesis. The update has the following form. You're going to update this weight vector if the hypothesis is incorrect for that input. You're going to update the weight vector by taking its old value and adding to it the class label times the input, right? Now, this is a pretty dramatic output. Some implementations say, don't do this hard update, update it some fraction like 0.5. So you'll see some sort of, Greek symbol that says only updated a fraction called the learning rate. But in this case, we're just going to do the full hard update just to show you what it's doing. And then in a future assignment, we'll tinker with learning rates and show you how that makes a difference, because that slows down your search. With this update, it's going to make large jumps, right? So it's going to take a hypothesis and it's going to take a dramatically different one. That's too jagged. It's like driving a car and, kind of jerking the car back and forth. When you add a learning rate, that's kind of smooth it down. It's going to kind of, make it move through the hypothesis space more smoothly instead of jerking forward and backwards. Okay, so let's take a look. In this example, we have our X, it's in vector form, right? And then we have our W, it's in vector form. Now, W transpose X, that's the inner product. If we take the inner product of W with X, it projects onto X in the negative direction. And here we have the ground truth label as +1. So that means sign W transpose X is negative, but the ground truth label is positive. It's an error. So what do? We say W is equal to W plus Yi times Xi. Y is positive, ground truth. X is here. So we take this vector, we multiply it by 1, and we add it to where that vector is. The new value of W is here. right? So if we take that new value of W and we take this value transpose times X, it projects on the positive side. We've now corrected that error. Does that make sense? Likewise, if ground truth class label was negative, well, here's X, here's W. W transpose X, it's positive. The label, it made a mistake. So now we say W, the new value, is W plus YI XI. YI is negative, ground truth, so that becomes negative. So we take that vector, we add it here, and now the new value of W is there. If we take this transpose with X, it's now on the negative side, so now the hypothesis outputs the right -1. Okay? Now, this will work, but it's a little bit too abrupt, right? It doesn't produce smooth solutions because, as we saw with the hypothesis set, good solutions, and we'll learn about this property when we talk about regularization, are solutions that move only slightly, not jumping really far every time it makes a correction. So this is called the perceptron learning algorithm, or PLA. And essentially, every time you do this output, what happens is if you select this input that's misclassified and you update this weight based on this xi, what it does is it moves the decision boundary to find another function or hypothesis such that this is corrected, that error is corrected. So you can imagine this line is going to get pulled around, adjusting itself to fix errors. Now, in fixing one error, it might damage another one that was correctly classified. That's why learning rates are important. Now, of course, this works well when you have a class of data that's so-called linearly separable. And I'll explain what that means another time. It's now time. Okay, so on the homework, and I'll pick back up with this on Wednesday, on the project, you'll be implementing PLA with a linear model using a two-dimensional data set. We have two features. Okay? All right. So I'll see you all on Thursday. Yeah, Thursday. All right.